So now that we know how to find a spanning tree in a graph, and we know that there are several different spanning trees, one of the things that we're going to look for is what's going to be known as the minimum cost spanning trees, or sometimes is abbreviated as the MST. So let's take it maybe go on to the next page. So for each one of these graphs, we're going to find the MST, or the minimum cost spanning tree. So in these graphs, there's going to be a bunch of different trees that we could find. Out of all of the different possible spanning trees, we're going to try to find the spanning tree then that has the least total weight. Now, there is an algorithm that will tell us what the minimum cost spanning tree is, and it's going to be very similar to that cheapest link algorithm that we looked at when we were solving those traveling salesman problems. Now what this algorithm says to do first is we're going to pick the lowest cost edge available and mark it. Now in case of a tie, meaning there's two of those lowest edges, just are going to grab one of them. And then for step 2, pick the next lowest edge and mark it. Now that feels very similar to cheapest link, where we kind of got those first 2 edges kind of quote unquote for free. So here's where we're going to have to start being careful. When we go to step 3, we're going to continue picking and marking that cheapest unmarked edge that will not create a circuit. Now when your tree spans or touches each of the vertices, you are done. At the end, you will end up with n-1 edges. Now keep in mind, when you execute this algorithm, you do not want to create any circuits, and you do not want to include all the edges. Now this algorithm is going to be pretty cool on a couple different levels. One, it's going to be fairly easy to run through it, and it will solve the problem quickly, so it's going to be an efficient algorithm. The other thing that is especially nice about it is it's an optimal algorithm. Running through Kruskal's algorithm will always give us that minimum cost spanning tree. Now keep in mind, when we ran the cheapest link algorithm when solving TSPs, we weren't guaranteed when we ran the cheapest link to get that optimal solution. We only found one that was an approximate solution. So here's going to be a change that's going to be a nice one for us finally, as we can run through an algorithm fairly quickly and it will always give us that best answer. Also keep in mind a new thing about this algorithm, that it's okay to have 3 edges coming out of a vertex, you just don't want to create any circuits. So remember with that cheapest link algorithm, you had those 2 different rules you had to follow, so not creating any circuits and that 3-edge rule. The 3-edge rule doesn't apply on Kruskal's algorithm. So let's see this applied in a couple different examples. So for each one of these below graphs, we're going to find that minimum cost spanning tree. Now in order for me to be able to check your work, I am going to ask you to record your weights in the order found. On this graph right here, then let's go and find that smallest weight. So it looks like it's going to be this 42, which I'm going to mark it, and then I'm going to record the weight. The next lowest weight is going to be this 45. I'm going to mark it and record the weight. Now at this point in time, any edge that I grab, I have to make sure it doesn't create a circuit. The next lowest weight is going to be this 49, and it's going to be okay to grab that. That doesn't create a circuit. Next lowest weight after that would be 51. Now I have 2 different ones of them, but this 51 is no good, because if I were to grab it, it would create a circuit right here. This 51 though is going to be okay. Let's see, the next lowest weight after that is going to be this 53, and that one's going to be okay. That does not create a circuit. After that 53, it looks like it'll be this 55, but that would create a circuit right here, so that one's no good. After the 55 would be the 56, but that would be no good because that would create a circuit right here. So then after that, looks like it's going to be this 59. So now I have spanned, I've touched every single vertex in the graph, so I'm done. This is going to be my minimum spanning tree. Let's go ahead and add up all of these weights then. So the overall weight for this minimum spanning tree is going to be 299. Now I want you to note from some of the calculations that we were doing before, this graph right here had 1, 2, 3, 4, 5, 6, 7 vertices. Okay, so the tree, that minimum spanning tree, is going to have n minus 1 or 7 minus 1 or 6 edges. I have 1, 2, 3, 4, 5, 6 edges, so that's being satisfied. This original graph, if you were to go through here, this original graph is going to have 12 edges. So the redundancy of this graph is 12 minus n minus 1, or 12 minus 6. So the redundancy of this graph is 6. Which means then when I find that spanning tree, we'll have 6 edges that have been omitted. And you can see here there's 1, 2, 3, 4, 5, 6 edges that we left off. Let's try applying Kruskal's algorithm again to this next example. So in this graph, the lowest number I'm seeing is this 60. So we'll mark it and record the weight. The next lowest number is the 65. We'll record it and record the weight. Now, from here on out, we're going to have to be careful not to create circuits. The next lowest number after that is 72, which I'm actually seeing occur both here and here. So at that point in time, it would be your choice. Grab one of them. And then from there on out, then it might make your graph look different than somebody else. But on this one, we're actually going to see if I grab this one and record it. The next lowest number is going to be this other 72, and this one's also fine as well. So I'll end up grabbing both of those. Okay, but if you see that lowest weight kind of repeated twice, grab one of them, and then from there on out, there's where your graph might look a little bit different depending on the choices that you made. But on this one, I'll be able to grab both of them, so we'll be okay. The next lowest number after that is 75, which doesn't create a circuit, so I will record that. After that, looks like 80, which occurs twice, but this 80 is no good because that would create a circuit right here. This 80 is going to be okay though, so I'm going to record that one. The next lowest number is this 85, but that's no good because that would create a circuit right here. After that is 90, that one's going to be okay. After that is the 95, that's no good because that would create a circuit right here. For the next lowest after that's going to be 100. That one's going to be okay. After that's the 105. And then the 125. And then finally this 130. Okay, so this overall spanning tree then has a weight of 974. Now again for this graph, there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 vertices, which means then there will be 12 minus 1 or 11 edges in the spanning tree. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that satisfies that count. In this graph, the number of edges in the original graph was 14. So the redundancy of this graph was 14 minus 11 or 3. So I had to remove 3 edges to turn this graph into a spanning tree. And you can see the 3 edges that removed are right here and here and here. Okay, so after seeing these 2 examples, I would encourage you to try this third one on your own. So for this one that we've actually looked at several times over this unit, for this graph, go ahead and find its minimum spanning tree. And after you've had a moment to kind of run through this algorithm on your own, then go ahead and compare that with the solution that I'm going to go over right now. Alright, so first off, maybe we'll do this calculation to begin with. So for this graph, there are 5 vertices. That means its spanning tree will only have 4 edges. In this original graph, there are, if you go through here, 10 edges. That means the redundancy of this graph is 10 minus 5 minus 1, or 10 minus 4, or 6. So ultimately we're going to get rid of 6 edges and we're only going to keep 4 of them. Running through this algorithm, the lowest edge is going to be this 119. The next lowest edge is 120. After that, the next lowest edge is 121. The next lowest edge after that would be the 133, but if I were to grab that, it would create a circuit right here, so that one's out. After that, it would be the 150, and that one's going to be okay. So there are my 4 edges that make it into my spanning tree. And this minimum spanning tree then ultimately will have a weight of $510.